These 15 points have exactly one triangulation worth building. This one. It's called Delaunay, and it's how a scatter of height samples turns into terrain you can actually stand on. Because here's what you get if you just connect the dots. Same points. Same 18 triangles. And it's junk. Look at these needles. Fit a surface through those and the heights you read between the samples are wrong. And the difference between the two is one rule. Not an optimizer, not a heuristic. One geometric test, 8 lines of code, that turns that into this. 3 points, 1 circle. This is Delaunay Triangulation. Here's why. Triangles are how you turn scattered samples into a surface. Say these are heights, and you want the height right here. You'd blend the corners of whatever triangle you're standing in. That needle has a name, by the way, a sliver, and 2 of its corners are way off over there. And this point, nearer than either of them. And it doesn't get a vote at all. The fat one asks the neighbors that actually matter. Same point, same samples. And look what comes out, 173, where the real height is 180. The sliver said 127. Here's why, seen from the side. A slice through the ground, right through that point. That's the real hill. The sliver throws one straight chord across the whole span and cuts under it. The fat one hugs it. So the shape of the triangles isn't cosmetic. It decides how good every number you read off the surface is. Take any 3 points that aren't in a straight line. There's exactly 1 circle that goes through all 3. The circumcircle. Every triangle has 1. Now here's the rule. A triangle is allowed if its circle is empty, no other point inside it. This one, empty, allowed. That's the whole rule. Now try a skinny one, its circle is enormous. And look, it swallows this point, not empty, rejected. See why the rule hates slivers. Squash a triangle flat and its circle balloons out. So it almost always swallows something. Keep it fat and the circle stays tight. Empty circles and fat triangles pull in the same direction. And a triangulation where every single triangle passes the test. That's Delaunay. Look, 6 points, 5 triangles, 5 circles, and not one of them has a point inside. 4 points sitting like a diamond. 2 ways to cut them into triangles. This diagonal or that one. One of them is Delaunay. One isn't. Test the first, circle through these 3, and the 4th point is inside. Fails. So flip the diagonal, and now check both circles. Empty and empty. Passes. Notice the flip nudged the angles the right way. The sharpest corner in the pair went from 35 degrees to 37. 2 degrees. Barely anything. But it isn't luck, and it isn't just this quad. Watch. Of every way you could carve up a set of points, Delaunay is the one that makes the sharpest corner in the whole mesh as blunt as it can possibly be. So here's the first algorithm, and it's almost embarrassingly simple. Start with any triangulation. This mess will do. Now look at each edge that's got a triangle on both sides. If the circle test fails across it, flip it. Keep going until nothing fails. Watch the smallest angle in the corner. Circle. Fails. Flip. Circle. Fails. Flip. Every flip is local. 2 triangles change and nothing else moves. And each flip leaves those 2 better than it found them. The number in the corner only jumps when a flip happens to hit the current worst triangle. 17 flips, and there's no edge left that fails. From under 3 degrees to over 20. This is Lawson's algorithm. From 1977, 40-odd years after a Russian mathematician called Boris Delaunay wrote the rule down. And it always finishes. Run it back to the start and watch the mesh get better. Every flip trades a worse pair of triangles for a better one. That's also why it stops. A flip strictly improves the 2 triangles it touches. So once you've left an arrangement of edges behind, you can never come back to it. And there are only so many arrangements. so sooner or later there's nothing left to flip. Flipping fixes a triangulation you already have, but you can also build one right the first time, one point at a time. This one's called Bowyer-Watson, and once you've seen it, you'll never forget it. Start with one giant triangle around everything. It's scaffolding. We tear it out at the end. But while it's up, every point we drop in is guaranteed to land inside some triangle. Drop in the first point. Now ask, which triangles have this point inside their circle? Just the big one so far. That triangle is broken. Throw it out. That leaves a hole. Connect the new point to every corner of the hole. And you've got triangles again. And every one of them passes the test for the points that are in so far. Next point. Same 4 beats, point, circles, hole, fan. Find the circle that contains it, throw that triangle out, and fan the new point to the rim of the hole it leaves. Now here's where it gets interesting. This one lands inside 2 circles, so 2 triangles break. Out they both go, and look at the hole they leave. It isn't a triangle anymore, it's a 4-sided pit. Fan the new point to every corner of it, and the mesh closes up again, and again, and again. Notice it's usually only a few triangles that break, the ones whose circles happen to reach the new point. The rest of the mesh doesn't even notice, and it doesn't have to. A new point can only spoil a circle it actually lands in. Point, circles, hole, fan. Point, circles, hole, fan. Last thing. Pull out the giant triangle, and every triangle that was leaning on one of its corners. What's left is the Delaunay Triangulation of the 6 points you gave it. Nothing borrowed, nothing left over. Same thing on the bigger cloud, sped up. Keep an eye on the count in the corner. 1 triangle to start with, and every point adds exactly 2. 15 points. In they go. Everyone breaks a few triangles, patches the hole, and moves on. Tear out the scaffolding. And there's the mesh from the start of the film. 18 triangles, every circle empty, built in 1 pass. Now watch this. That's the mesh flipping crawled its way to, laid straight on top, and it lands on every single edge. 2 completely different algorithms, 1 answer. And that isn't luck, barring ties. 4 points sitting on 1 empty circle. A set of points has exactly 1 Delaunay triangulation. There's only 1 place to land. Here's the whole build in Python. The algorithm itself is these 10 lines. The rest is that 1 circle test and some arithmetic. And it runs. Start with the giant triangle. The code calls it the super triangle. Then, for each point, the bad triangles are the ones whose circle contains it. And here's the whole. Take every edge of every bad triangle and keep the ones that turn up exactly once. An edge that turns up twice was shared by 2 bad triangles. That's an inside edge, and it goes. Throw the bad ones out, fan the point to the rim, and once every point is in, drop anything still touching the super triangle's corners. And there they are. The 8 lines I promised you at the start. The circle test is the only real geometry in the file. Find the center of the circle through the 3 corners, and ask whether the point is closer to that center than the corners are. Everything else is bookkeeping. Now, 2 things this code won't tell you. The first is speed. It checks every triangle against every point. That's fine for a few hundred points. It gets sluggish at a few thousand, and it's hopeless at 1,000,000. Real libraries walk straight to the triangle they need, instead of scanning them all. The second, the scaffolding has to be genuinely giant. Here's a set of points, and it's Delaunay mesh. Watch what happens if I use a scaffold that's merely big. That triangle circle is huge, huge enough to reach a corner of the scaffold, so it never gets built, nor do its 2 neighbors. And when the scaffold comes out, it takes a bite of the mesh with it. Nothing warns you. The 10 in the code, 10 times the widest spread, is plenty for anything in this film. Real libraries put the scaffold at infinity and stop worrying. Now, one more thing, and honestly, this is my favorite part. Every triangle has its circle, and every circle has a center. Put a dot at each one. And remember what that center is. The one spot that's the same distance from all three corners. Now join the centers of neighboring triangles across every shared edge, center to center. And think about what each center is. No one point owns it because three of them are tied for nearest. It's a border post. Out at the edge of the mesh, where a triangle has no neighbor to join to, the line just runs off the page. You've just drawn the Voronoi diagram. Each cell is the territory of one point. Everywhere on the plane that's closer to it than to anything else. Which phone mast you're talking to. Which shop is nearest. It's the pattern on a giraffe, more or less. And the regions in a procedural world map, exactly. Delaunay and Voronoi are the same information, drawn twice. So, 3 points make one circle. Allow only the triangles whose circle is empty. And the fattest triangles the points can give you fall out for free. Got a bad mesh? Flip its edges. Starting from nothing, drop points in and patch the holes. Either road, same mesh. And the centers of those circles hand you the Voronoi diagram on the way past. Once you know the circle rule, you can't unsee it. The mesh under a game's terrain. The grid a physics solver runs on. The rooms in a dungeon generator wired up. Same handful of empty circles, every time. That's Delaunay Triangulation. 3 points, one circle, and keep it empty.